So today we are talking about volume of a solid when we have semicircular and triangular cross sections as opposed to squares and rectangles last time. And I actually found a good image of this. So I'm going to share my screen and pull that up really quickly. So these are what the 3D shapes that we are finding the volume of looks like. So hopefully you can see a little bit clearer using these lovely pipe cleaners that the region on the bottom is the area between two curves. And then we have all different types of shapes that are cross sections to the area between the two curves. Like here we have triangles, over here we have semicircles, right here we have squares, but those could easily be rectangles if they were a little taller. So hopefully this visual helps you in terms of seeing what these shapes look like, because I know that my art is seriously lacking. So hopefully that helps you out. So that being said, let's move into the lecture. So we are comfortable with finding the volume of a solid whose base is the area between two curves using square and rectangle cross sections. Unfortunately, our cross sections are not always squares or rectangles. Sometimes they're other shapes like semicircles and triangles. For instance, consider the graph of x plus y equals 1. Let's say that the region below this graph in the first quadrant is the base of some 3D figure. Further, we know that the cross sections of this figure perpendicular to the x-axis are semicircles. What is the volume of the 3D figure? So we're going to draw it, and I want you to take a second. So just as we did when we had square rectangle cross sections, we are going to think about finding the volume by, well, think about this for a second. Pause the video, and what was the general process that we used to find the volume of a solid with square rectangle cross sections? And see if you can apply this process to find the volume of the figure that we are about to draw. Okay, so I want you to try this potentially, but we are going to go through it together. See if you can figure it out though. Think about it as like a challenge to yourself. But anyway, so we have the line x plus y equals 1. It's easier if we see that in y equals mx plus b form. So we'd have y equals negative x plus 1. So if we have our coordinate plane right here, y equals negative x plus 1 is going to be a line like that. Okay. And then what else do we know? Okay. We know that cross sections of this figure, so here's our region R, that base right there. And we know that cross sections perpendicular to the x-axis are semicircles. So I'm going to do my very best to draw this. So I'm going to have the base right here, and then coming up is going to be a semicircle. So it's going to be like, look like a D almost. Or it actually looks exactly like an uppercase D. So here are semicircles. And hopefully you can kind of picture, the base of this region is this triangle, and then coming up, we have these semicircle cross sections. And just like we did with square and rectangle cross sections, we are going to take these little slices and give them some depth. Okay, so I'm going to focus in on one of my middle slices so you can really see it. I'm going to erase the other ones. So here's our middle one that we're going to focus in on. This cross section is coming up towards us, and it's a semicircle like this. And what we're going to do is we're going to add some depth to this semicircle. So we're going to add a little bit of depth right here. And perhaps predictably, we are going to call that depth dx, just as we did with squares and rectangles. And so if you were to take the slice and look at it from a different angle, it would kind of look like this. So we have like a 3D little slice right here. And then this diameter right here is your area between the two curves, right? So this base right here, I'm going to put it in green, corresponds to this right here, which is the area between the two curves, which is going to be, as we know, top minus bottom. So top minus bottom in this case is negative x plus 1 minus 0, because our axis is just, because the base of our figure is just the axis. So top minus bottom is just going to be minus 0. So that's just going to be equal to negative x plus 1. So we know that the base of our semicircle cross section is going to be negative x plus 1. And then we're just going to think about this the exact same way we did square and rectangle cross sections. So we know that volume is equal to area times depth. Depth is dx. And so area is going to be area of our semicircle. Okay, so area of semicircle is going to be 1/2 pi r squared. If it was a full circle, that actually wouldn't really work. But since it's a semicircle, we are going to have our area of our circle, pi r squared, and then 1/2 of that because the circle is split in half. So that means we need our radius. And we know already that this is diameter. And we know also that diameter is equal to radius divided by 2, or diameter over 2 is equal to radius. So if we know our diameter, then our radius is going to be that negative x plus 1 divided by 2. Okay, so we have our radius now. And we can go ahead and plug that into our equation for the area of a semicircle. So it's going to be 1/2 pi times r, which is negative x plus 1 over 2 squared. And then our depth is dx. So here I have the equation for one little 3D slice of semicircle, but we don't want the volume of just one little slice. We want the volume of all of the slices. So in order to find the volume of all the slices, we're going to do a nice little integral, and that will be the integral from, we're starting here at this x point is 0, and then this x point is 1, as you would know if you set x plus y equals 1 equal to 0. So we're going to have the integral from 0 to 1 of 1/2 times pi times negative x plus 1 over 2 quantity squared dx. And you can actually solve this integral. This one isn't as messy as some of the ones that we were solving with squares and rectangles. You can actually solve this whole thing out by hand, and you would get pi over 24, an exact answer, which the homework asks for. So be on the lookout for that and have fun evaluating some integrals by hand, even though I know that you can do them in your calculator. We want exact answers for these, and I will post work. So we will go over in class the homework, and we will also look at some work. Okay, let's move on to triangular cross sections. So to start, we want to try and imagine that we have some shape, the base of which is the region between two curves, f of x and g of x, and whose cross sections are triangles, where the hypotenuse of the right triangle is the distance between our two curves. So instead of doing a specific example for this one, we're going to use the process that we know to find a general expression for finding the volume of some figure that has triangular cross sections. So let's start with a picture. So here's our axes, right? And we are going to have this be our origin, 0, 0. And our functions are going to be f of x in green and g of x in blue. Okay. And then we are going to label this other point up here where the two functions intersect, c, d. So we are told that, like right at this top here, f of x and g of x intersect at 0, 0 and CD. The cross sections are isosceles right triangles with a hypotenuse as the distance between the 2 points. So I'm going to do my best to draw this again. So here's one of my cross sections. Oh no, I didn't want to do that. So here's one of my cross sections, and this is going to be the hypotenuse for a right triangle that's going to kind of come up, or that's kind of gonna come up towards me like this. And there is my right angle. My hand got really shaky there. So I'm gonna do another cross section here. And then it's gonna be another right angle, kind of like this. And then let's do one more down here. And so we're gonna have a right angle, kind of like that. My hand is shaking so much. Those lines are so squiggly. And then hopefully you can kind of see that it's kind of like a almost like a blimpish structure. If you were to think about like, okay, the base of this is this flat eye-shaped thing, and then you have triangular cross sections coming up towards you. So again, if you need to reference the image at the very beginning of this to see this a little bit better in your head, please do that. Okay, so we know we're going to take one of these cross sections and we're going to add a little bit of depth. So I'm going to draw this guy as 3D. I'm going to add some depth here. So there's some depth right there. We have a 3D little slice of triangle. I'm going to try to draw this separately over here. I'm going to have this right triangle. I'm going to draw it a little bit 3D if I can do that. That's pretty bad, but hopefully you can kind of tell that I was trying. And we also know that the cross section is an isosceles right triangle. So you probably don't remember this, but a property of an isosceles right triangle is that these two side lengths are going to be equal. Okay, so we're going to call this length A. And this is also going to be A because they're equal. We're going to call this guy H because it is the hypotenuse. Okay, so our two side lengths are A and our hypotenuse is H. The hypotenuse, we know, is top minus bottom because the hypotenuse on this image right here corresponds to this length right here on our picture. So yellow to yellow. And so that means, since we're doing a general problem, top minus bottom is just f of x minus g of x. Okay, so the bottom is the hypotenuse, which is just f of x minus g of x. And now we're going to use a well-known property of triangles to figure out some more information, and that is the Pythagorean theorem. So we know that a squared plus a squared equals h squared. Okay, so we can rewrite that as 2a squared equals h squared, and then a squared equals h squared over 2. Okay, so then a is therefore equal to the square root of h squared over 2, which is equal to, I'm going to rationalize that. So if I have the square root of h squared over 2, that's equal to the square root of h squared over the square root of 2, which is equal to h over the square root of 2. But I do not want a radical in my denominator, so I'm going to have h over the square root of 2 times square root of 2 over square root of 2, which is going to give me h square root of 2 over 2. That was all algebra 2, so that's why I went through that very quickly. And I can rewrite a as h square root of 2 over 2. Okay, so take a second. Hopefully you can follow those steps. You learned that in Algebra 2, and I know that because I'm teaching it right now in Algebra 2. Okay, so we know what the length of A is in terms of H, which is something that we also know because we know that H is top minus bottom. Okay, so if we were trying to find the area of this triangle, we know area is equal to 1/2 base times height. Okay, except for now we know that base and height are A, and further that A is square root of 2h over 2. So we can rewrite this as area equals 1/2 of h square root of 2 over 2, h square root of 2 over 2. Okay, and then we can multiply this whole thing out, and that equals 1/4 h squared. Okay, and finally, we know that h, in fact, is top minus bottom, which is f of x minus g of x. So area is equal to f of x minus g of x squared over 4. Okay, and then if we want to make area 3D, aka if we want to turn area into volume, we add some depth. So I'm going to switch colors so this is apparent. Volume equals area times depth. And we know our depth is dx, that little guy right here, dx. And so area is f of x minus g of x, quantity squared over 4 dx. And then if we want the volume of the entire 3D figure, again, we integrate from, in this case, 0 to c, which is a general point. So this is the What we have in yellow is the general expression for finding the volume of some figure that has triangular cross sections. Okay, so we will be you have 4 homework problems. They're going to be difficult. I want you to try your best on them. Try to work them out. We can go over them in class, and I have all the work for them that I can also post. So bring your best attempts to class, and we will talk about it then. Hopefully the picture helped you to see these more clearly, and other than that, have a wonderful day. I'll see you in class.